Welcome back to the Kubernetes series. In the last video, we explored why Docker alone isn't enough for production machine learning systems. We saw the real world pain points, scaling issues, no self healing, configuration chaos, and rolling update nightmares. Now, it's time to move from theory to practice. In this video, we are going to start building our Kubernetes foundation from the ground up with hands on example that will make it click. Here's what we are going to cover today. Step 1, Kubernetes architecture. We will break down master versus worker nodes, the control plane, etcd, scheduler, and kubelet, so you understand who does what behind the scenes. In step 2, we'll look at core objects. We will dive into pods, replica sets, deployments, and services. And I'll explain why Kubernetes uses pods instead of containers and how these objects fit together intuitively. In step 3, we will look at local Kubernetes setup. So we will set up a local cluster using MiniKube, go over kubectl basics, and run a cluster sanity check to make sure everything is ready for hands-on experiments. And in step 4, we'll get our first hands-on, where we'll deploy a Dockerized app, expose it to the network, scale it up and down, and even kill a pod to watch Kubernetes self-heal in real time. And by the end of this video, you will have a working local Kubernetes environment and the intuition to understand what's happening under the hood. So we'll stop talking and we'll start building our first Kubernetes cluster. We will first start by understanding the backbone of Kubernetes and its architecture. At a high level, a Kubernetes cluster has two types of node, the master and the worker. The master node is like the brain of the cluster. It identifies what should run, where, and when. It keeps track of the cluster's state, makes scheduling choices, and ensures everything is working as expected. The worker nodes are like the muscles. They run the actual workloads, our pods, our ML services, our apps, and they follow the master's instruction and report back on their status. The master node itself is made up of several key components known collectively as the control plane. And first, we'll talk about etcd. Now think of etcd as a distributed key value store. It's the cluster memory. Every piece of information about the cluster, every configuration, every desired state lives in etcd, and it is the single source of truth. Next, we'll see the scheduler. Whenever you create a new pod, the scheduler chooses which worker node should run it. It considers resources, availability, and constraints, making sure everything is balanced and efficient. Then the kubelet. The kubelet now runs on every worker node. It's like the master's personal assistant on that node. It ensures the containers inside pods are running correctly and reports the status back to the master. And together, these components make Kubernetes self-aware, self-healing, and intelligent. Unlike Docker, where you manually start and stop containers, Kubernetes knows the desired state of your system and constantly works to maintain it. And this architecture is what allows Kubernetes to scale, heal, and manage complex ML systems reliably. Once you understand this, everything else, pods, replica sets, deployments, services, starts to make perfect sense to you. We'll try to make sense of what we just said using this Kubernetes architecture figure. We learned that a cluster has a master and worker nodes. The master node, or the control plane, acts as the brain, making choices and storing cluster state in etcd. It schedules workloads with the scheduler and ensures everything matches the desired state via the control manager. The worker nodes are the muscle running your actual workloads with the help of kubelet, kubeproxy, and the container runtime. At the heart of it are all pods, which hold one or more containers and share network and storage. And with this architecture in mind, everything else we'll learn makes much more sense because we'll know who does what behind the scenes. Now that we understand the architecture, let's dive into the core Kubernetes object. the building block that makes your cluster run smoothly. First up, pods. You might ask, why not just use containers? Well, a pod is the smallest deployable units in Kubernetes, and it can hold one or more containers. The key idea is that containers inside a pod share the same network and storage, making it easy for them to communicate and work together. Think of a pod as a single logical unit. Your ML model container, for example, could live inside a pod. And if you want a sidecar container for logging or metrics, it lives in the same pod. Next is the replica set. A replica set ensures that a specified number of identical pods are always running. If one pod crashes, the replica set automatically spins up a new one. So instead of manually restarting containers, Kubernetes handles it for you. It's the core of self-healing. On top of that, we have the deployment. Deployments provide a higher level abstraction over replica sets. They manage updates, rollouts, and versioning. If you want to deploy a new model version without downtime, the deployment handles that automatically using rolling updates. So user never experience interruptions. And finally, there's the service. A service provides a stable network endpoint for pods. Pods can be ephemeral. They can die and restart they can die and restart elsewhere. But the service ensures that your app is always reachable at the same IP or DNS name. For ML inference, this means your API is always accessible even if pods come and go. And together, these core objects let Kubernetes orchestrate containers intelligently. You define the desired state, how many pods, which version, which network rules, and Kubernetes takes care of the rest automatically. Understanding pods, replica sets, deployments, and services is key before we move on to hands-on cluster setup. And once you get these concepts, deploying, scaling, and maintaining ML applications become much more intuitive. Now that we understand the architecture and core objects, it's time to set up our local Kubernetes environment so we can get hands-on. The popular option for running Kubernetes locally is MiniKube. MiniKube spins up a single node Kubernetes cluster in a virtual machine on your laptop. It's simple and great for learning. Once you have your cluster set up, we'll use kubectl, the Kubernetes command line tool, to interact with it. Think of kubectl as the bridge between you and the cluster. It sends command, queries status, and helps you deploy applications. But before we start deploying, we'll perform a quick cluster sanity check to make sure everything is working. We'll check that the nodes are ready and that the control plane is accessible. So here's what you need to do step by step now. At first, we are going to install MiniKube. So for that, open your terminal and then simply type winget install kubernetes.minikube. This should take you to the installation process, and once that is complete, then we'll try to install kubectl. Okay, so the package is already installed in my system, and then it tried to upgrade it, but no upgrade was found. Once your MiniKube installation is complete, make sure you have Docker Desktop on your laptop installed and running. So with this, we're going to start MiniKube using the following command: MiniKube start driver close to door. So once the MiniKube is started, then we'll move on to kubectl, and then we will check our nodes using kubectl. We will try to understand what actually happens when we run MiniKube start. Think of MiniKube start as pressing the power button of a complete Kubernetes cluster on your local machine. Behind the scenes, the single command does several things at once. First, it creates a virtual Kubernetes environment using Docker. That environment acts as both the control plane and the worker node, all inside one local cluster. Then it sets up the entire Kubernetes architecture as we discussed earlier. The API server, the scheduler, etcd, the controller manager, and the kubelet. It also configures kubectl to talk to this cluster automatically. So when you run kubectl commands, they are sent to this MiniKube cluster by default. In simple terms, running MiniKube start is like saying, create a mini production like Kubernetes cluster on my laptop and make it ready to accept workloads. That's why MiniKube is so powerful for learning. You get the same concepts, the same architecture, and the same behavior as a real Kubernetes cluster, just scaled down to run locally. And now that our cluster is up, we're ready to verify it's working and start deploying real applications. Once the cluster is up, the first thing we want to check is the nodes. We do that using the following command: kubectl get nodes. So this command asks Kubernetes a very simple but important question. Which machines are part of my cluster and are they ready to work? In our case, with MiniKube, we usually see one node. That single node represents both the control plane and the worker running together on your local machine. The most important thing to look for here is the status column. If it says ready, then it means Kubernetes is running correctly, the kubelet is healthy, and the node can accept pods and run workloads. If the node is not ready, Kubernetes won't schedule any applications on it. So this step is our sanity check before deploying anything. Think of it like checking if the engine is running before driving a car. Once the node is ready, we know our cluster is alive and we're ready to deploy our application. So after we have checked the nodes, the next step is to verify the cluster itself. And we do that using the following command: kubectl cluster info. This command gives us high-level information about Kubernetes cluster and confirms that control plane is reachable. And when we run this, Kubernetes respond with the address of key components like the Kubernetes API server and the core custom services running inside the cluster. In simple terms, this command answers the question, is my Kubernetes cluster alive and responding? If this command works and shows cluster URL, it means that the control plane is running. kubectl can successfully communicate with the cluster and the cluster is ready to accept deployments. Think of this as checking the dashboard light after starting a car. If everything lights up correctly, you know the system is operational. And now, with both the node and now, with both the node status and cluster info confirmed, our local Kubernetes environment is fully set up and we are ready to move on to our first real deployment. Now that our Kubernetes cluster is up and running, it's time to interact with it for a very first time. We're going to start simple, no deployment, no scaling, and no self-healing yet, just a single pod. This step is important because a pod is the smallest unit that Kubernetes can run. But before we talk about automation and resilience, we need to understand this basic building block. So here I have opened a new project folder on my computer, and inside this folder here, I'm going to create a new YAML file. So you can name it anything you want. I'm going to name it pod.yaml. So now this file will contain the instructions that we want to give to the Kubernetes. And remember, in Kubernetes, we don't run commands to start containers. Instead, we describe what we want and Kubernetes figure out how to make it happen. So now we'll write this pod.yml file here. So first I'm going to include API version v1. Then I'm going to write kind and then mention pod here. Then in case of metadata, I'm going to say the name of this. Let's name it demo pod for now. And for its spec, containers, name. So let's call it demo container. The image will be nginx, and then the ports of the container port will be 80. So before we apply this file, let's understand what it actually does. So this YAML file tells the Kubernetes to create one pod, and inside that pod, run a container using the nginx image. And once we apply that, Kubernetes will choose where to run the pod, pull the Docker image if needed, and start the container for us. Now let's go through this file line by line and understand what it actually does. So the first line, API version, specifies which version of Kubernetes API are we using. And for pods, the stable and commonly used version is V1. The second line tells Kubernetes what type of object we want to create. Here we are explicitly saying that we want a pod. Then in the third and fourth line, this contains information used to identify the object. And here we're giving our pod a name called demo pod, so we can reference it later using kubectl commands. The spec section defines the desired state of the pod. What should be running inside it? And here the section defines the list of containers that will run inside the pod. So even though this pod has only one container, Kubernetes still expect a list here. Now here, this is the name of the container inside the pod. It helps with identification, logging, and debugging. This tells Kubernetes which Docker image to run. So Kubernetes will automatically pull the nginx image from Docker Hub if it's not already present on the node. And finally, this indicates the container listens to on port 80. And at this stage, the port is only accessible inside the cluster, not from the browser yet. So one very important thing to understand here is that this is just a single pod. If this pod crashes or gets deleted, Kubernetes will not recreate it. And that's not a mistake. It's exactly how pods are built. The limitation is what leads us naturally to higher level objects like deployment, which we'll cover next. So for now, remember this, Kubernetes doesn't run containers directly, it runs pods, and a pod is powerful, but on its own, it's not enough for real production systems. It is now time to actually apply our pod.yml to our Kubernetes cluster. And this is the moment where we move from theory to reality. So let's go to our terminal and then enter the command kubectl apply minus pod.yaml. So this command will tell Kubernetes to read the instruction from our YML file and then create the resource inside a cluster. We're not starting a container manually, we're submitting a desired state to Kubernetes. So let's run this. Okay, so this output confirms that Kubernetes has successfully accepted our request, and at this point, Kubernetes has stored the pod definition and started the process of scheduling and running it on a node. But this doesn't mean that the pod is already running. It just means that the Kubernetes is now responsible for it. So to observe the pods, we get to kubectl get pods. So here, this is the name of the pod, exactly the one we defined in the YML file. This shows how many containers are really inside that pod. So 0 out of 1 means there is no container running here yet. And then the status we can see here, the container is being created here. And then right now it is 0 for the restarts. So This actually shows how many times the container inside the pod has restarted. And then the age tells us how long ago the pod was created. So meanwhile, while this is being created, let's again check the pods and then see once its status is ready. Okay, it's still being created. So I'll check after a few minutes here and then see if the container has actually, especially on the first run, we might briefly see the status as container creating here. And this is completely normal because Kubernetes is pulling the Docker image and then setting up the container. And once that process is complete, the status will change to running here. Okay, now the status has changed to running. So what actually happened when we ran this command here? So the API server accepted our request. The scheduler chose which node should run the pod. The kubelet on that node pulled the Docker image, and then finally the container was started inside the pod. But right now we have exactly one pod. So if this pod crashes or we delete it, Kubernetes will not recreate it. And this limitation is intentional here because pods are not built for self healing. And this is exactly why we need higher level abstraction like deployments, which we will move to next. So yes, we've successfully run our first workload on Kubernetes, but uh, production Kubernetes does not stop at pods, and this is just the beginning here. Okay, so before exposing anything, let's first confirm that the application is actually running inside the pod. So for that, I'm going to use the command kubectl exec it demo pod, which is our pod name, curl, then localhost. So this command executes a request from inside the pod itself. So let's run this. And then once we run this, we can see our default uh, Nginx HTML page here. So this confirms that our container is working perfectly. But the problem here is not the application. The problem here is accessibility. Now let's try accessing this from the browser itself. So if I go to localhost or the MiniKube IP in the browser, nothing happens at first. And this is kind of expected here. So a pod is isolated in the Kubernetes network right now. And by default, Kubernetes does not expose pods to the outside world. And this is a feature here, not a bug. So we now have a new problem. Our application is running inside Kubernetes, but it's invisible. And this is where Kubernetes services comes into the picture. So a service provides a stable network endpoint for one or more pods. So it acts as a bridge between the internal Kubernetes network and the outside world or between pods inside the cluster. And services solve several problems at once. So the first one is that pods can come and go, but the service stays at the same IP or DNS name. And traffic is load balanced across multiple pods, and you no longer have to manually track pod IPs. So for now, we will use a simple service type called NodePort, which exposes the pod on a port of your local machine so we can access it from our browser. So let's type the command kubectl expose pod, provide the name demo pod, and then I'll provide the type as NodePort, and then the port that I'm trying to expose is 80. So this command tells Kubernetes to take the pod named demo pod, expose port 80, and then assign a node port so that it can be accessed from outside the cluster. So if I run this, Kubernetes automatically chooses a port. Okay, what is this? I have an error here. So let me first fix this error. Type equals to node port, demo pod, expose demo pod. The pod has no labels and cannot be exposed. Uh, okay, the error makes sense because Kubernetes services actually uses labels to know which pods to route traffic to. And in our pod, demo pod does not have any labels here. Uh, so Kubernetes cannot figure out which pod the service should point to. So let's update our pod.yml. Down below the name, let's insert labels, and then inside this label, and give app and demo here. So to use this, let's go back to our terminal. Let's delete our old pod. So kubectl delete pod demo pod that has already been created. A resource type PDF. Let's see once again. Did we save this part? Yes, we did. Now let us select our pod here. So what pods are running? No PDF. Sorry. So kubectl delete. It should be pod, not PDF. Pod and then demo pod. Okay, so now this is removed, and then we want to apply our old pods again, the pod.yml again, the updated pod actually. So now that is updated, and then if we can go to get pods, now this has been created, and once it's running, then we will try to expose the pod again so that it can be accessed from the browser. So let's check again. Okay, now it's running. Now let me type the command kubectl expose pod demo pod, and then the type is equal to output. When the port I'm trying to expose is 80. So service demo has been exposed. So now we can check the service using kubectl get svc. We can see that our demo pod is running on a cluster IP here. So finally, since we are using MiniKube, we can do MiniKube service and then demo pod, access the pod of our browser. Okay, MiniKube spelling it wrong. So MiniKube service demo pod. Now a page has been opened in my browser, and then it basically shows welcome to Nginx, which we saw in the HTML file before. So our application is now running in Kubernetes, and it is accessible from the outside world. So here we didn't have to worry about pod IPs or container ports or manually mapping anything. Kubernetes takes care of routing all traffic to the correct pod. And this is why services are so powerful. They actually decouple your application from the pod, making scaling and self-healing possible without breaking connectivity. So now that we have a stable pod running and exposed, now it's time to level up. So a pod by itself is very fragile. If it crashes or is deleted, it's gone. And Kubernetes won't bring it back. And that's fine for learning, but in real world systems, we need reliability and scalability, right? So this is where deployments come in. So a deployment is a higher level Kubernetes object that manages pods for you. It ensures that the desired number of replicas are running, automatically replace pods that fail, and then allows us to scale or update the application without downtime. So now let's convert our single pod into a deployment. Here we'll start with one replica. It is essentially the same as our current pod, and then later we scale it to multiple replicas. So now let's go to back to our folder and then create a file called uh, deployment.ynl. Okay, so here now I'm first going to do API version. Let's do appsas v1. The kind here I'll mention is as deployment, metadata, name. So this is going to be demo deployment. Okay, and then inspect. I'm going to do replicas one selector, and inside selector, I'm going to match levels. And inside this, the app is demo. The template here, we use the following metadata. So the labels here will have demo. And then finally, on the spec side, let's define containers, kept in the list. So provide name. Let's call it demo container. The image here will be Nginx. And then the ports to be exposed will be container port, and then I use it here. So here I'll try to explain what we just wrote. So first of all, this API version tells Kubernetes which API version to use for this project. So deployment belongs to app/v1 API, which is stable and then recommended for production. So the next, this specifies the type of the object we're creating. Here we are creating a deployment, not a pod or a service. So deployments manages pods and provides scaling, self-healing, and polling updates. Now, this contains identifying information here. So we're giving our deployment the name or demo deployment, so we can reference it later using QCTL. So the spec section defines the desired state of our deployment. Here, replicas equals to 1 tells Kubernetes to maintain one pod at all time. So even if that pod crashes, the deployment will recreate it automatically. Now, the selector tells the deployment which pod it manages. So it matches the pods that have the label applicable to them. And this is why labels are essential, and without them, the deployment can't track pods. Now, below this, the template defines how the pod should look. So every pod created by this deployment will get the label app equal to demo. So it matches the selector we just defined. Now, just below this, we have the spec inside the template that talks about the container that will run inside each pod. So here the container name is the demo container. It uses Nginx Docker image, and then it exposes the port IP inside the pod. So this is essentially the same container we ran in our standalone pod earlier, but now it is managed by deployment. So now let's apply this YAML file here in our terminal. So to do that, I'm going to do kubectl apply -f -n deployment.yml. Okay, so there is something wrong here. Error when created to render as a deployment given cannot be handled as a deployment, strictly decoding. Okay, so I think I have some typo here. Okay. This should be spec, not SEPC. It should be SPEC. And again, here also suppose it should be spec. So let me try to apply this again. Again, I think I have something wrong here. So let me check what mistake I made, and then we'll go and apply this. I found the error that I made. The template here should be in the same label as the selector. The metadata should be in the same label as match labels. And then the label should be in the same label as app demo. And this will go one step earlier. So again, this spec is going to be in the same label as metadata, container in the same label as labels, and then all of this will just go ahead with one step each. So now let me save this and then try to reapply this deployment.yml again. Okay, so now that this is applied, Kubernetes creates the deployment object and then automatically spins up a pod according to the template here. So if we want to check the deployment, we can do kubectl get deployments. And here we can see that the deployment, it's desired replica and then current replicas and then the ready replicas. So now if we do kubectl get pods, so uh, we have our pod created by the deployment here too. And then we also have our old pod that we had created earlier. So here, the main thing to understand is the difference between the pod and a deployment. So a pod is just a single unit that Kubernetes runs, and then a deployment manages pods, keeps them alive, and allows scaling or rolling updates. So even with a single replica, we now have self-healing, and then if this pod crashes, Kubernetes will automatically replace it. They will also do what we just said about the part of self-healing. So here, when I do kubectl get pods, then we can see a deployment pod being deployed. Now the name here is auto-generated by Kubernetes, and then it contains the deployment name plus a unique suffix. So now what we're going to do is we're going to delete this pod. So to do that, I can do ctl delete pod, and then I'll just copy this name. Let me check if I can auto-complete this or not. Okay, I cannot auto-complete this. So here I'm just going to copy this, Control C, and then I'll paste it here, Control Shift B. So what we're trying to do here is we're intentionally deleting the pod to simulate a crash here. And normally, if this were a standalone pod, then it would have been or it would have gone forever. But with a deployment managing it, what Kubernetes will do is Kubernetes will immediately create a new pod to replace it. And to verify that, let's do kubectl get pods with this minus w here. So as you can see, we already have this uh, deployment pod rerunning again once we deleted it. So this is self-healing in action, and this is one of the core benefits of deployments in Kubernetes. And even with just a single replica, Kubernetes ensures that our application stays available all the time, and we no longer need to manually restart crashed containers. So the deployment will handle it automatically. So now that we've proven self-healing works for a single pod, let's scale our deployment to multiple replicas. And this is how Kubernetes handles real-world applications with multiple instances running at the same time. So scaling is as simple as changing the desired number of replicas here. So Kubernetes will automatically create or remove pods to match that number. Now to do that, what I can do is do kubectl scale deployment and then provide the name demo deployment, which we provided in deployment.yml file, and then provide replicas equals to 3. So this command tells Kubernetes to maintain 3 replicas of this deployment. It will create 2 new pods in addition to the one that is already running here. So let me run this. So the replicas should be created now. Let's check our pods here using kubectl get pods, and then we can see that in addition to one demo deployment pod here, 2 new replicas of it are being created. So here all the 3 pods are actually running the same container image, and then each of these actually have a new name. So with deployments, Kubernetes handles both self-healing as well as scaling automatically. And this is foundation of uh, production grade MLOps systems. Now you can run multiple replicas of your ML model, safely handle failures, and then serve traffic reliably. We will now also see self-healing working in multi-pod scenario here. So if one pod crashes or is actually removed, Kubernetes will immediately replace it without accepting the other running pods here. So if one pod crashes or is removed, Kubernetes will automatically replace it without affecting the other running pods. So that will ensure our application remains highly available. So now we can see that our free running pods are part of the same deployment. So let me just delete one pod here. Okay, I'll delete this first one. So to do that, I can do kubectl delete pod and then directly provide the name of that pod. So here we are going to simulate a failure by deleting one of the pod, and then watch how the Kubernetes responds to this event. So let me do kubectl get pods again. And you can see that once we deleted that pod, kubectl or the Kubernetes actually recreated uh, another pod just 12 seconds ago here. So the deployment immediately restored the design number of replicas, three in this case. The other pods continue running without interruption here. So that is self-healing being activated at scale. So with just a few command and a deployment, Kubernetes actually ensured high availability, automatic recovery from crashes, consistent application state across replicas, and this is exactly what makes Kubernetes production ready for ML workloads or any other web application here. Now, another important feature of Kubernetes is that it allows us to scale our deployment up or down at any time. So, and the best part is that our service automatically distributes traffic across all running pods. So, and that is exactly how production grade systems handle the running load without downtime. So, let me is in this replicas to actually type replicas here. So let's do kubectl here. Scale deployment. So demo deployment, and that I set replicas to fire. So if I do get pods here, I should see 5 different pods here. The three were already running, and then the additional two are being created. Uh, so now let me do MiniKube service and then demo pod. So it will expose our page to the browser. So if I keep on refreshing this, even though I see the same page here because just one service, the Nginx service is being created, but what's happening in the background is that each of these requests are being routed to different uh, pods among these 5 pods here. So Kubernetes service load balances traffic evenly across all these running replicas. So that means we can safely scale up to handle more users, or like if we have less users at some time, then we can scale down to save our resources without any manual intervention. And to scale down, we don't need to do a very complicated process. We just need to scale our demo deployment and then set the replicas to maybe 2 pods here right now. So if I run this and then if I see kubectl get pods, then I can see that remaining 3 deployment pods are being removed And then we only have two replicas running at the current time. So the service is actually adjusted automatically. So traffic continues flowing seamlessly to the remaining pods. So with just a deployment and a service, we now have self-healing where crashed pods are being replaced, where scaling, where increasing or decreasing replicas on demand. We have load balancing where service is spread, uh, or like service basically spreads traffic automatically, and we have zero downtime, meaning user never notices any changes behind the scene. So this is exactly how real world ML inference services, web apps, and APIs run in production. And that's a wrap on our first hands-on Kubernetes session. So today we started from a simple pod and learned how to expose it to service. And then we upgraded it into a deployment, giving us the power of self-healing and scaling. We saw how Kubernetes automatically recreates crashed pods, how to scale our application up and down, and how a service actually spreads traffic across multiple replicas. So this is exactly how production paid systems run ML models, web apps, or APIs reliably and at scale. So with just a few commands, we've already experienced the core magic of Kubernetes: reliability, scalability, and high availability. And in the next video, we'll dive further, deeper, truly run production grade MLOps workloads on Kubernetes. So make sure to try all the commands yourself, experiment with replicas, and then see self-healing, self-healing in action. It's one of the most exciting parts of Kubernetes here. So if you enjoyed this video, hit that like button, subscribe, and turn on the notification so you don't miss the next episode of our Kubernetes MLOps series.